The
God.
announcement the other day, NVIDIA is pretty spectacular right now.
We are. I think we are
Oh,
live.
we got lucky for
Oh,
sure.
hey, we're live. Greetings, fellow nerds. Welcome to another episode of Between Two Nerds, where we talk with prominent guests about all aspects of the networking industry, from protocols old and new to industry trends and drivers to up-and-coming technologies, and as always, things you need to know to further your career. Jeff, good to see you again.
Jeff, good to see you too. Been busy
Oh.
days, and we always find time for each other, right?
Yeah. So we, as those of you in the audience probably could tell, we got obsessed with talking about the weather instead of anything networking oriented. But we've got a really good topic, and not only a great topic, but a great topic for probably several shows moving forward here. And we've got a very prominent guest with us. We're very happy to have Petr with us. Do you want to introduce yourself?
Of course, thank you, Jeff. Thank you for inviting me to the show. My name is Petr Lapukhov. I go by Peter. It's spelled as Petr, as Jeff said. Peter is so much easier for the audience. So for last 10 years, I've been working on various parts of web scale infrastructure. First at Facebook, before that was at Microsoft. So it's always networking, automation, software, operations. And the last 6 months, I was at NVIDIA, where I joined after Jeff Tantsura, who was ahead of me. But most of the time, we still spend on the same topics: future of networking architecture, GPUs, and AI infrastructure. And that pretty much occupies most of my time in the last 6 months.
Great, thank you. So our topic, as I think everybody can sort of determine from what was just said, is on AI data centers. We're going to be talking about AI data center design and what are the requirements behind that. But I think a good place to start, and Jeff, you've got some good slides there. But I think to really understand the drivers for AI data center design and the unique requirements. In some ways it's unique. In some ways it's just it's still just typical network design. But to understand that, we probably need to understand AI ML workflows. Would you agree with that? Would you guys agree with that?
Yeah, I mean, same network design is still there, right? It's just the cost of doing it incorrectly is completely different.
Right. And I mean, we're dealing with massive. That's probably where most requirements come from. Is we're dealing with massive data sets when we're talking about machine learning training and inference, and of course before that, just massaging the data sets to a point where training can take place, and that has a huge impact on how you design the networks behind this, right?
And I think another angle to look at this is speed of change, right? 2 years ago, we were talking about 4K cluster, 4K. Yeah. When I say K, I always mean GPU, so pretty much switch ports.
Yeah.
Right? It sounded really, really large. Last year, suddenly 1632K became a topic. This year, we are deploying 100,000, and 2 years from now, 500,000 million. So imagine each GPU is usually connected to at least one switch port, if not two. So this is number of switch ports deployed. And in the first two layers of data center, we don't oversubscribe. So you can count amount of switches, complexity of connecting it all together, and what would happen if you just build your artisanal routing schema that has a bunch of ECALs, bunch of policies, mutual redistribution, and whatnot, right? You do it for your enterprise, probably will survive, right? No one will even notice when you fail stuff. You do it for AI training, something fails. Most fundamental thing, or most operations are collective. So even if 99% of your network is great, but 1% is not, you are going to be at performance of that 1%, which will incur huge cost and potentially get you fired because of that. So no pressure, but
no pressure at all. It's only your job. Yeah, and I mean, both of you guys are with NVIDIA, and this is a great opportunity. I think this is just to establish this foundation because NVIDIA pretty much owns the AI oriented. Is that the right word? The GPU market. I mean, there's certainly other manufacturers out there, AMD and all of that. But if you look at market share and all of that, NVIDIA is just the 800-pound gorilla in the room, and so you guys are the authorities on the servers, the GPU clusters that are doing this processing. And a first question, maybe for viewers that are not really sure, or maybe just very new to the topic, is something that's maybe kind of very obvious, but why GPUs? You think of GPUs as graphic cards. It's right there in the name. Why are GPUs suddenly the foundation of processing clusters?
Probably we can split the answer. I would say we should go back in time, probably 12, 13 years ago. And when
we need to do the little Bill and Ted sound effect.
When AI was over, I mean, it was an academic topic, right? People have been researching since early 60s.
Mm-hmm.
Practically in 2012, I believe, AlexNet was designed and brought, right? This was the first time when data set was larger than the amount of memory on the GPU that could hold it. And they've shown that by parallelizing the job across more than one GPU, you can actually do training faster with higher fidelity. And I think this is where it all started. So I'll let Petr explain what a GPU is. Probably the better person.
Oh, sure. There's a lot of explanation online. I guess what NVIDIA got right historically by chance and by strategic thinking, first they designed accelerators for the graphics, which happened to architecture which was massively parallel. Mm-hmm. So you had lots of little cores, which aren't as good as branch prediction or caching, but very good at executing lots of simple instructions in parallel on say data which represents textures or polygons and everything else. And at the same time, when people realized there's a lot of parallelism in machine learning, like data parallel training, or mass multiplication, matmos, Jensen and the company released the API, which opened SDK to researchers to run the matmos on GPUs. Effectively, it's very simple to say, run matmos on GPUs. The API, the CUDA API was pretty straightforward to program in if you compare to SIMD concepts. And that, I think, enabled GPUs to overtake this niche of massive parallel computations. Remember, in the 90s, it was like machines like Cray. They were also massive parallel, right? Highly specialized for vector operations, right, on matrices. But GPU was like a small supercomputer, right? Thousands of cores, okay, maybe hundreds initially, but allow you to run your code with high level of parallelism. So that, I think, allowed early researchers to train the models on GPUs, which wasn't initially natively optimized for that, right? And training is an operation which is naturally parallelizable by data parallelism, and there's a lot of multiplications there because of the structure of a network. So that coincidence was very lucky, I think. Machine learning needed massive parallelism, and GPUs had it in time. So they became the synonym, right, of machine learning infrastructure. even though early on, people only used like one GPU initially, right, for training, very quickly realized you can partition the model across, not model data, across multiple GPUs and scale this pretty straightforward fashion using data parallelism. So I think it was a very opportune moment that NVIDIA took on in time and made GPUs the de facto infrastructure for training. And after some time, most people get used to it. They keep evolving the whole ecosystem around it. CUDA, cuBLAS, cuDNN, all the libraries came up, and it became even more solid, right, for all the infrastructure work. But remember, this is a networking topic. Back when it was not networking, right? It was just like GPUs on PCIe bus, right? Networking came a bit later when people realized it's easy to parallelize training using data parallelism, right? You take a bunch of data, like images, split them in mini batches and feed them to different GPUs, and then aggregate the outputs, which was the essence of early parallel training. And that required a network, right? Initially, a network which was like, say, perhaps just TCP/IP, right? You connect multiple machines together and shuffle the data, the gradients across. And also, to be fair, like early on, GPUs weren't the only one for structural training. Like when Kepler came out, I think Google trained a lot on CPUs, and so was Facebook, because CPUs were abundant, right? One is massive parallel, but you can bundle lots of CPUs together, like over network, which was the paradigm back then. Unfortunately, it wasn't as efficient, or fortunately, depends on who you look at, right? As just trying to take a GPU, which was just already a massive parallel processor, and use it in a big pool of resources. But fair enough, the early training methods used large CPU pools. If you look at historical training, look at parameter servers, and Google all the papers from Google Brain. It was all CPU based, using TCP/IP networking and so on. But later on, they started evolving at a very fast pace and specializing very quickly. But we'll get there. I just want to say a quick history tour in GPUs and mention that it wasn't the only infrastructure for training. They became de facto dominant because of its super high performance, right? Because of massive parallelism of architecture.
Yeah, and it's that parallelism. I can't say the word parallelism, but that really is at the bottom of network requirements. Well, you pretty much said that. If you're spreading your processing, your training across many GPUs, and it's a surprising number of GPUs in some AI data centers these days. You've obviously got to have the network to support that parallelism. Maybe I'll learn how to say that by the end of the show.
So I think we're going to use few slides kind of to provide context for everything we are going to discuss for the next couple of hours.
Yeah. And I do have one question. This is actually a question just for me because I don't really know the answer to it. Is we were talking about GPUs, and you mentioned Google. Google uses something called TPUs, tensor processing units. And I don't actually know myself. Does anyone other than Google use a TPU?
I think
no. Sorry, Google doesn't disclose. I mean, they publish papers, but they don't sell it out as a silicon. From what all I know, maybe somebody does.
Yeah.
But they sell it as a cloud service. The TPU was designed, I think, around the time frame when NVIDIA had Kepler K80 GPU, and it was trying to optimize one operation, multiplications, right? Which was very special architecture, very simple by on purpose, which I think they got right back then, in my opinion. It was easy to say this is optimized for modmoles, but unfortunately, it wasn't as flexible to accommodate future workloads, which are very rapidly changing. I think it works fine, but if you ask me, programming a GPU is much more straightforward at the architecture level than CPU. Yeah. And there's still a big debate, of course, whether TPUs are more efficient per dollar, per watt, than GPUs. That we can't resolve here. Of course, we believe GPUs are more efficient. and way more programmable than CPUs. But CPU, I think, is a wonderful architecture that stood the test of time over last over 10 years, right? I think when Google started this 2016, 17,
15,
I think we got it, got it like in time because they needed realize that, well, we need something optimized for our workloads. And back then, I think, what was it? They already had language models, right? Early language models, RNNs, and of course CNNs, visual models. Back then, it was nothing like today. It was image processing. Language was some on the outskirts of research, and was ranking models, like recommendations, to try to predict what you want to click, which is a big thing for Google, Netflix, Amazon, of course, Facebook. But CPUs are there, right? I think it's one strong. You mentioned early on, whatever silicon is, of course, NVIDIA. Well, with TPUs, and that probably mentioned AMD is also one market player, and the plethora of startups who are doing also additional products. But as far as I know, they aren't as popular, nearly popular as the first three.
So I would think even so, Google was the company publishing a white paper on transformers. Practically, I don't think anyone could imagine the speed models are going to evolve. And, hardware life cycle is much longer than that of model development. So potentially, you kind of need to use your crystal ball to think, how are models going to look next year, potentially next year, because hardware life cycle is in years. It's definitely not in days or months, like software. So practically, when it's difficult to change your hardware or potentially some parts of the hardware to be aligned with new architecture, with new model, this is where you might, if not lose market share, at least not grow as fast as someone else who built products that can actually address something completely new. That, moving to MOE or using kind of experts architecture, broad performance, almost an order of magnitude, right? So, but hardware need to be able to accelerate this. And if it's not, you fall behind. I'm not talking about Google. It's kind of very general comment. You need to be able to foresee what's coming when developing hardware.
Actually, a general comment on Google strategy, it's hard to do it alone, right? When you have your own ecosystem, it's you to support it. NVIDIA's choice of opening the software infrastructure, I think, was a huge one because it allowed it to grow from all the contributions worldwide. Well, maybe it was probably the best idea to give it to researchers. Even though many times you give something to research, it never pans out, right? But that time it really, really pans out into something big. Now ecosystem around GPUs is humongous, right? It's really hard to match it. So I can imagine how much it takes efforts for Google to maintain their ecosystem, right? Which is quite different. And you see how it evolves. Look at TensorFlow V1, V2, and PyTorch, how things keep flip-flopping between the preferences people have for the frameworks. So it's not like it's just my experience was this observation, just very subjective. It's very nice in the beginning. You build your own infrastructure, your silicon, which is great, a lot of fun, by the way, a lot of good ideas. But then you realize you're doing this almost in isolation, alone, right? Because no one else is doing the same thing. And it's hard to keep pushing forward because, well, things may change, right? Workloads may have changed, and you have to modify your architecture. And the fun part, GPUs are very generic, right? GPUs are very generic. It's not like an ASIC, which is specialized for specific operations like matmos, like CPU was. It's pretty generic in things it can do, right? Using its instruction set. So it helped GPUs to be much more flexible and add, optimizations on the way. Like Hopper had transformer engine, and Ampere had memory copies, async memory copies, and other nice things we keep adding. Volta had tensor cores. So the general architecture remains the same, always like bunch of threads and accelerators on the side keep evolving. But I think it was a pretty big thing that NVIDIA got right conceptually. Architecture for accelerators kept evolving. It was never changed fundamentally. It remained the same. Just pretty nice surprise it was such a good fit for machine learning operations.
And being open played significant role, said Peter.
Oh.
So the CUDA has been open since day one, and this is pretty much de facto standard today. Our communication library, Nickel, is open source. Source code is available on GitHub. You can go read it, see it, how it evolves. It's really, really important because it's kind of fundamental to how your training is going to work, right? So being open and kind of getting feedback of community and evolving this way has been fundamental for quality and speed of development.
And somewhere, whether it's this show or a later show, we probably should talk a bit about CUDA, and how much. I'm personally curious, how much CUDA really is an influencing factor on NVIDIA's dominance in the GPU market. I've read some stuff saying, it's not so much the GPU, it's CUDA. And I don't know if that's true or not.
It's a combination of great software and great hardware. There's a lot of company, right, building good hardware, but without software, it's meaningless. I mean, imagine router without BGP, right?
Yeah. So somewhere along the line, after we get a little bit further into the basics, we should talk a little bit about CUDA. Same thing with Nickel, and what is Nickel, and how that library influences how a data, how you design a data center, an AI data center.
Okay, so let's.
Sorry, GPU and BGP have something in common. It's GP in both of them.
Yeah, there's actually a lot of commonalities, right?
Yeah.
Both around the world.
Bad joke. Okay, let's go. Let's do some slides. I don't want to derail conversation.
Yeah, let's see your slides here, Jeff.
Yeah. It'd be shiny. Awkward moment.
Too many clicks. Yes. So let's start from the beginning. And Peter, please interrupt me. Right? It's not a feat.
Anytime, of course.
Yeah. So what drives the network size? And it's true for both neural network as well as network as topic of the discussion, right? It's really model size.
Mm-hmm.
So what you see here is the kind of evolutionary picture published by Microsoft probably about 18 months ago. And you could see how scaling to more parameters requires more GPUs, right? For very simple reasons. You need more memory to load less parameters. I mean, you could have less core and run training longer, but you need to be able to load the model. If you don't have enough memory, you just don't have enough memory. It's like regular computer. If you don't have enough RAM to load the program, it's going to fail. So practically, after first LLM came out just a bit more than a year ago, it became very clear to whole of industry that this is just the starting point, and we see more and more proof that overtraining or training model longer on the same data, or training it on the same data, but more scalable hardware, more allowing hardware provide better results. So this is information published by Meta. I said recent because it's like about 6 months old when Meta presented last networking scale. Mm-hmm. And you could see amount of information or model size and how many GPUs it took to complete and how many hours it took, right? So we are talking about close to 1 million hours to train Llama 2, which is 70 billion parameters. So it's 2K A100 GPUs. Potentially, if you run it over 4K GPUs, you would be faster, but there's cost of distribution that is non-obvious. If you run it on something like H100, which is the next generation after A100, it wouldn't take you 1.7 million GPU hours, but potentially half of it. So you see by having not necessarily always wider. You could do scale up by introducing more scalable hardware. You can train faster. Training faster means you're faster to the market. Really, it's not just research and white papers that behind our real money. Because the better your model is, the better services you can provide. I mean, in case of Facebook or Meta, it's somewhat different than if you're public cloud, but still your main goal is to train highest quality model in least amount of time. So this is...
So I want to add one thing, Jeff. It's not just model size, it's time to conversion, time to solution. Well, there's not plus conversions because you have to add more GPUs. Of course, fit in memory. First time you have to fit in memory model. How did you fit it? But then you need more parallelism to simply train faster, right? Because the whole essence of train was always data parallelism. Of course, it became more complicated over time. It was like, let's create n replicas, throw different data shards to replicas, when they all negotiate gradients and continue together. And voila, your acceleration is n times, right? You have n times more parallelism. It's actually Amdahl's law. Actually, it's Gustafson's law, because you keep throwing more batch, more data as a scalable system. So this was actually what made, I think, AI training so efficient compared to HPC, classical HPC. It was like weak scaling. You can do nearly linear efficiency improvement as you add more GPUs. Of course, you have to do a lot of work to make it more efficient. Like at some point, you run out of data to throw GPUs. The batch size is limited. You have to add more dimensions of parallelism, as Jeff will talk later. But there's always, I think, the holy grail of AI is that, look, you can train faster if you add more GPUs. It doesn't like flatten like an Amdahl's law. It keeps scaling near linearly. Some work, of course. Well, lots of work, to be fair. But people are like, well, look, we can train bigger model, which takes more time to train and more tokens. We're talking here about, of course, LLMs. But you can do so faster by adding more compute. But unfortunately, well, depends for whom, once again. As you scale a model, time grows as a power law, time to train. And number of GPUs is linear. I mean, you can buy more GPUs. Of course, we always welcome that as a company. But you cannot really place them like at a whim. For space and power limitations. And I think it's going to be a big topic of discussion we're going to have. How the hell are we going to fit all these GPUs in data center? But that what drove, I think, this revolution in ML or deep learning, just a bit of simplification, of course, but the fact that we can throw more GPUs at the problem and it keeps getting better and better. If you look at this exponential growth of the last few years, that's in a very simplified manner, of course, what drove it. Bigger model, more GPUs trained faster, right? And converge faster. So here we have Llama 2, like Llama 3 was trained on 800s, was I think another paper from Meta this year. There was, I believe, at least 16K GPUs, 16K, so 8 times more. And rumor is OpenAI has it even bigger, but we don't publish much, so it's only rumors. But we also know that at least Elon Musk stated they're building big clusters, bigger and bigger. And of course, the whole goal is more parallelism. You can just like take these all GPUs and try to scale your performance nearly linearly, the number of GPUs, which is very shocking, right? You always used to, like, well, you add more threads, you have Amdahl's curve, it kind of flattens at some point. But here, it's a holy grail, right? You can just keep adding more and train faster. Sorry for this digression, Jeff, but I wanted to point out that pretty important to point out networking serves as a glue to get always GPU pulled together, like humongous GPU pulled together.
And I think main point of what Peter said and those pictures is that AI clusters will continue to grow. There's no reason not to grow them practically with newer models and training methodology and more capable hardware. You're going to be able to train faster with larger data sets and come to solution resolution much faster than before. So practically for networking folks who are listening to this is just the beginning. Data centers are not going to get smaller. They might potentially get sparser because of power consumption, some space consumption, but in total number of endpoints, number of switches you need, number of layers in a network is only going to grow. So there's no stop in sight. So again, we are at fundamentals. Let's take a look at how training is happening. So we've got a lot of data. With no data, there's no training. We've got a training cluster, which is a set of GPUs that are connected both internally and externally. They're high power, high memory. So each new generation of GPUs has more memory. And training could take any time practically based on the complexity of the model, the fidelity requirements, and it could be anything. It could be in months, could be theoretically in years. Actually, I'm not familiar anything that runs for years, but why not? So after model has been trained and meets your fidelity requirement, it's embedded at the edge. It requires much less power, memory, and less networking actually. Have very different requirements with networking. So latency becomes fundamental, but it's less. It is important. It's always important, high performance networking. But in inference, it becomes really, really important, right? The response time is very important as well, right? Because now we are not interacting with machines. In most cases, we are interacting, in a LLM case, with either human or person on the other side of the query, or some kind of API that eventually will interact with the person, right? So, we are losing, as a human beings, attention within probably 100 milliseconds, right? So first word must show between 10 to 50 milliseconds. Next following 4 words in the sentence need to be there in the same amount of time, right? So if you don't generate output fast enough, the consumer of this information will just move on. It will use someone else's product. It will do something else. It's very similar to early problem with slow web loading, right? If it takes too long to just get website on the screen, you would just move to another website, right? So it's somewhat similar from human behavior.
By the way, I want to add that latency, I feel, will become a pretty important constraint for machine-to-machine inference. Because today we assume that LLMs would emit some text to a human, but in the future, we all think it's going to take off. You may have applications calling other applications to do the inference, and there it doesn't matter. Like, there's no human anymore. You want to get response as fast as possible. So token latency may become pretty important, right? We're at very early days of all this product building out of LLMs, and compared to what you used to before, LLMs are pretty slow at inferencing because computation is humongous, right? To do with single token, emit single token. But I feel that in the future, it becomes a very important constraint, of course, both on compute side and networking, because inference today becomes a multi-GPU problem. You have to partition the model across multiple GPUs, and to increase the inference speed, you have to partition even more to get more compute for the inference. And as we all know, optimizing for latency is always harder than for bandwidth. Bandwidth we're used to. Networking is always history of bandwidth. You double it, you triple it, but unfortunately here it won't help at some point. Latency or propagation of processing on every GPU becomes important constraint for inference. And as we all believe in the future of LLMs and AI, I believe inference will take a huge piece of a pie, right, for all the products. Today we train, like everything we talk about is training, big clusters. But at some point, if it becomes a real product, it would be inference that takes most of the volume. To be fair, I don't think it's the case yet, but if this wave takes off, this will become the next big hardware demand window for inference and optimized for human to machine to human, and machine to machine inference.
It's a great comment, and so this will potentially bring some changes to how we architect infrastructure for that.
Yeah.
Again, just repeat, Peter, it's much more difficult to optimize for latency and bandwidth. It's been true for networking since networking exists.
And I should mention that that it's important. You've got kind of a linear process here, taking the data, training it, coming up with a trained model, and then you've got inference. But this is important for being able to understand the flow. But what's also in here is that this is an iterative process. You don't just have your you don't just have your trained model and that's a final result. There's a constant flow back into data that's being processed to modify and make the trained model better, right?
Yeah, so I think it's a very important point, and I think this is what we've seen in the kind of proof tool that we've seen over the last 6 months. Supervised learning provides really great results over training model. So again, training model on the same data for longer significantly improves fidelity and quality of the model. So to your point, I think we'll see more and more iterations rather than this fixed window to retrain the model. I think we'll see more and more kind of intermediate steps to increase the fidelity, reduce, what is the right word? When you get incorrect answer, but it sounds so... Hallucinations.
Yeah.
It's really an important point to make outputs of a model like high fidelity, something you can actually believe. Because today, many people would use 3-4 different models and cross-reference them. And you get output of one, put another, see if it comes back with references. This is how you increase fidelity, because all models train on different data and use different algorithms to provide an output. Practically, I would like to be able to use any of them and be at least 99% sure that answer is correct. I get right references. And if it's incorrect, I would prefer answer, I don't know, I need more time to come back tomorrow, rather than, hey, this is what it is, I just invented it, but I'm so sure it's right.
Yeah. I like that. I like
so
that
I'm trying to
analogy.
use analogy too. Let's move on. So this is kind of to set the context for next couple of meetings. So AI networks are performance optimized. They are not cost optimized. We are not looking at saving $10 more or beat. Why is it? Any time network is in a way, you lose money. You lose significant amount of money. Infrastructure is really, really expensive. And you would like to get most of performance to your network rather than save some money. Right? It sounds weird, but if you look at cost of bit lost, cost of bit delayed, the consequences are severe. You might need to restart your job. You might need to go back, which really means that you just lost time. Something you've already trained might not be recovered, right? So when we build this network, we always look at maximum performance. Cost is secondary, and cost is really fractional as compared to total cost of AI cluster. What drives the networking? It's job completion time. This is really the main metric. And, we know from TCP that throughput is not good, right? Your throughput could be huge, your good could be nothing. Try to drop a couple of TCP packets and, you will see where your good put is. In AI specifically, good put doesn't necessarily result in shorter job completion time. So it's very important to understand when you are building and designing clusters that your target is how quick your job gets to its completion. And network should be the last place that gets in the way. Next point is, again, we've been trying to save kind of money and time to build by under subscription. It's much easier to bring more hardware or increase the amount of bandwidth available rather than building more intelligent network, right? It's not an option for AI networks. Really, utilization below 90% automatically means that network is getting in the way. If you look at H100 GPU generation, single GPU can generate almost 400 gig line of flow. Single flow, not 20 flows, just one flow that is of this size and long duration. So if your fabric cannot provide way to transfer it without dropping, transfer it without delaying it, you are losing time. On another side, however, power is the most constraint. It's not really whether you can get GPUs. It's not whether you can build anything. It's really power you can bring. That's kind of the main concern, because you're trying to build larger data centers or larger AI clusters. You are trying to cool it. You are trying to make sure that for the next 3 years, you're going to have enough power. And it's not the case. So practically, while you see that kind of conflicting goals, on one side, you are trying to say, I should put enough networking so it's never in the way. On the other side, you should always remember that every watt spent on networking is not spent on GPU. And GPU requires significant amount of power. Right? So it's very, very important to bring these contradicting goals together. So you would still like to have on networking side reasonably, I wouldn't say low, but try to lower power consumption while not kind of giving away the performance. So something to really think about. Next point, in traditional data center, there's one network. Right? Sometimes you might see different networks used for storage, but those are not necessarily common cases. In AI cluster, there are many different networks, and performance of all of this network is fundamental. So here we are talking about IP Ethernet networking. We've got scale-up networking, which is in NVIDIA NVLink. It has different kind of flavors, different vendors. Practically, usually, it's almost order of magnitude faster than external networking. It allows you to run a form of parallelism that cannot be run over Ethernet, just due to the fact that it's not fast enough, not quick enough. Most importantly, we are sharing memory. That's pretty much most of the work you do over NVLink or similar topology technology. Ethernet doesn't really have memory semantics, right? So you need to build an overlay transport that can emulate memory. The NVLink kind of technology has this semantics inherently, so it allows you to provide a memory sharing service. And
hey,
the last, yeah.
I'm sorry, just finish. I'll have the comments. Please go ahead, Jeff.
Sure. And the last thing, it's always platform play. It's a combination of communication libraries because they use different algorithms. They might switch from one algorithm to another when they distribute traffic. You need to have a NIC that is smart enough to completely offload, to provide zero copy, to provide GPU direct. So there's a lot of smartness that goes in the NIC. Otherwise, your performance is still that of CPU, because if CPU is in the way, things don't work fast. And then switches that can support this topology, this technology, can actually provide non-blocking transport for this huge flow, can live in an environment with very low entropy. Go ahead, Petr.
Oh, yeah. I wanted to give a few historical examples. So remember, like, was it 12 years ago, 14 years ago, 2010, Hadoop was a big deal. Always data storage, direct touch storage, and computational job MapReduce was a big deal. That was, in my mind, a precursor to this type of systems. And to be fair, back when they also built data centers at 100K scale, except for CPUs, not GPUs. And CPU has like maybe 2 orders of magnitude less cores. So you have like maybe 32 cores. Today you have thousands of cores on GPU. So it's a big delta, but same count of endpoint NICs, roughly speaking. Of course, back when speeds were 1G, today it's 800G, so something has changed. But the same principle, remained. We had distributed communications. Like Hadoop job runs on multiple CPUs. but it shuffles data from the disks, not from HBM. So bandwidth delta is humongous, of course, you can imagine. But it was using TCP/IP. So Jeff gave TCP/IP some hard time here. I think TCP by itself is okay as a protocol. Implementation was never optimized to be high performance. Right? TCP runs on CPU cores, always data copies and juggling, of course, make it less efficient at high speed. But otherwise, it's a nice protocol. And remember, it was even RDMA iWarp over TCP. Never took off. Sorry, Chelsea. But but like TCP by itself is not a bad protocol. And actually, if you look at how Rocky works, many ideas were come from TCP. And because after 40 years of work in transport, there wasn't many ideas left. You cannot, reuse or recycle. In my opinion, compared to Hadoop and GPU networks today, what changed? We actually have elephant flows, like Jeff said. I remember, in 2000s, I came to Microsoft. Well, elephant flows going to kill us. All these elephants and mices. I'm like, oh crap. Okay, let's look around. And it was okay. It wasn't a big deal. It was a big deal if you can simulate it by stress testing. But in reality, network wasn't a big blocker back then, unless you really paper it or subscribe a lot. So that changed a lot of GPUs, right? As Jeff said, with RDMA, and you can push at line rate, you have this very thick flow, and if it hits a link and link is same speed, well, you can get collisions pretty quickly, right? So I think when we started working on this, I think I was still at Facebook, we were like, well, we can probably try to use TCP/IP, right? Because we know how it works. Nobody wants to mess with RDMA. Rocky is very complicated and so on. And was one barrier. So back when GPUs talked network over NIC directly, so GPU direct was one thing NVIDIA got very early on, is to do data transfers from GPU memory directly to the network. Because remember, GPU was, for longest time, like a coprocessor on the wire. PCIe bus, CPU, GPU. I mean, these days it's evolving more into Grace our CPU and the CPU and GPU together, one complex. But back then it was just separate. It's an x86 CPU and GPU. And to start data transfer, you have to kick off a queue pair from a NIC from CPU and then do transfer from a GPU. But that was line rate, right? You can actually push it. I think Mellanox NICs were pretty good at that, just hogging your wire with bandwidth capacity, the bits on the wire. And first thing you experience actually elephant flows in the network. And simply using ECMP routing wasn't an option. You can't just stochastically load balance flows, they collide, and you see very quick cross degradation because you have collectives. So two flows collide, your whole collective is slower by 2x immediately, which was a pretty big deal. And that's something we have not seen that much in Hadoop days, right? So that took some time to resolve, right? Because we tried to use TCP/IP from GPU to talk to each other, wasn't efficient, right? Because TCP wasn't optimized for that, simply speaking, right? Kernel TCP/IP. And then I think we'll cover this in the other slides, Rocky and InfiniBand and other things, because Rocky is effectively RDMA is InfiniBand over Ethernet. Although a fun fact, a while ago, when IB was becoming an emerging standard, people were really like, well, this RDMA stuff was really shitty, super slow. We have message passing, this proprietary things, Firebase for HPC, which are much better, right? It's funny to look at these arguments back when people were like, all this one-way semantics is pretty crappy. We need actual message passing to it much MPI. I mean, MPI is still a standard in the HPC community. And Nickel actually copies MPI collectives, of course. But then it's funny to look back and say, people used to complain that RDMA was not performant or efficient enough. And I mean, now of course, things changed, but it's always fun to look back in the history and see how folks argue about semantic of protocols. But I also want to highlight one other thing, power utilization for the network. So over time, as we point out, performance can be addressed. You can, well, in most cases, you can optimize things, do proper routing, optimize transport, but power gets hungry every year. I think this is one trend that we've seen in networking. We build bigger and bigger switches, more and more bandwidth, but power grows super linearly, right, for all these devices. So every year, you have to allocate more power for networking. And the more you allocate for networking, the less you have for GPUs. So every time, every generation, you can put less GPUs and networking in the same data center. So this is what puts tremendous pressure on data center sizing. I think like 10 years ago, 12, it was like, okay, 30 megawatts is enough. 30 megawatts is crazy, right, for one building. These days, it's like, it's one room, right, 30 megawatts. Let's go bigger, let's go gigawatts. And network becoming a pretty big chunk of power tax there, right? Especially, we haven't mentioned this yet, NVLink, right? Networking, which is very, very dense. Bandwidth-wise, it's crazy. It's like 10x of scale-up, scale-out networking. So you have your Ethernet or AB. You have NVLink, which is 10x bandwidth, right, compared to Ethernet. And it's invisible so far. It was invisible so far because it was on the board. But now it's becoming actual rack, which has a network inside it. So I think this is one big trend we need to cover and discuss is how big of a deal network becoming for these systems. It's not just RDMA or IB or Ethernet. It's also this big fat NVLink pipe, which connects GPUs together. And that's one thing I believe Misa got very right from early on. This was a project in R&D at NVIDIA in Pascal times. They built this interconnect for the GPUs. And back then was like any strong example of similar technology built before. But folks took the risk and deployed it, and it became, I think, the essential part of the ecosystem now, NVLink. And now we have like how many generations, like 4 gens of this technology to connect the GPUs together. And that's a pretty big deal for this fabric. So if actually you have like this big fabric for lots of GPUs, inside every rack, you have mini fabric, which is very, very dense, right? It's much smaller, but much, much denser at the same time. So we should probably cover this in bigger details later on in the conversation because it's a very big deal, I think.
Mm-hmm.
It is.
So,
and if you look at what NVIDIA has been publishing, the current generation of servers, which is H100, has an NVLink domain of 8. So practically you have 10 times more bandwidth between GPUs in the server than you would have if you interconnect them over external Ethernet or InfiniBand network. NVIDIA has already announced next generation known as NVLink 72. So the NVLink domain has increased from 8 to 72, meaning you could have 10 times more bandwidth between 72 GPUs rather than 8 before, because NVLink or scale-up networking is so important for a particular type of parallelization.
And I want to jump in really quick because we've been talking a lot about RDMA, and Peter, you pretty much defined that, but I don't know if any of us actually said what that acronym is, which is Remote Direct Memory Access. And as you described, it's essentially how do you from the NIC directly access memory bypassing CPU and kernel that slow things down. Is that a reasonable?
Yeah. I think the biggest deal was that a NIC runs transport stack now, right? And that's a big deal. You have a mini stack on the NIC that implants connections, data shuffling, error recovery, flow control. That's like a mini network inside.
Yeah, so we all know what DMA is, right? Anyone who ever touched a computer knows. So RDMA or remote DMA brings semantics of DMA over the network.
Yeah.
So DMA is an operations memory, right? So usually your addressing is, so you're on the same server, so you'll have some kind of PCIe or some other type of address to write or read data from. RDMA allows you to read or write data to a remote host. So practically, you brought DMA semantics, but allow it to work over wide network. That's probably the most important part of RDMA. What is done on the NICs, it's called direct GPU direct.
GPU direct,
yeah, it's somewhat different technology. So practically, as Peter explained, normally, or not normally, on regular server, you would go from GPU to CPU, PCIe, and then network, right? And you would copy data every time. So speed-wise or efficiency-wise, it's really not a good proposition. With GPU direct, since you are instantiating transfer on the NIC itself, your NIC is capable of reading memory directly from GPU memory, writing it on the wire. So it's a zero copy, it's extremely fast, and NIC, again, as Peter explained, provides many validations, semantic validation, and it binds the operations of copying pieces of memory, providing resiliency, a lot of stuff. Probably not, it's too deep to discuss here. Practically without zero copy and GPU direct, you wouldn't be able to use current generation of GPUs on the network. It would be just too slow and too cumbersome. So again, it's pretty fundamental for high performance. How are we doing on time? I don't see time because I'm.
We have about 5 minutes left before the top of the hour.
So let me just cover first slide of parallelizations, and probably it's a good point to stop and restart next time. So most common parallelization hierarchy or technique in the AI clouds is data model and tensor parallelism. In recent time, there've been more parallelism, going even more granular than tensor, that might include expert parallelism, some other techniques. Practically, those are three kind of fundamental types of parallelizations that define traffic patterns and whether you use scale out or scale up networking. So communication library is fundamental to allow communication across more than one GPU. So as we said, this work started really early when we figure out we actually can use more than one GPU to compute faster. And again, it goes back to AlexNet that happened somewhere in Canada. I believe it's either Toronto or Vancouver University. And people figure out if I put a couple of GPUs instead of one GPU, I can load larger model because I have more memory. I can also compute faster because I have more cores and I can run computation in parallel. So communication library is fundamental to be able to train larger models. It's an open source work by NVIDIA, so it's available on GitHub. There's huge amount of great data on the developer NVIDIA.com Nickel. And again, there's probably weeks worth of material reading. It's a fascinating topic on itself. And this will be the last slide for today, at least on my side. So we process data in batches, right? And we look at the amount of memory to load all the data. However, if we can pass all the data into memory of a single GPU, there's really no need for external networking. If we use DGX-like server that has 8 GPUs and NVLink for inter-GPUs communication, same comes here. If you have enough memory, you don't really need external networking because all the exchange of gradients, all the parameterization, forward and backward runs are happening between GPUs. If you don't need to go externally, you do it on the single server. And back to inference, this is what you see a lot today because inference requires much less compute power and memory. In many cases, you will see single 8 GPU server doing it, right? Because again, latency on NVLink is just one fraction of what you would see on scale-out network. So while again, this is quite common, especially in inference space, it might be good enough for small models. It's really not the topic of all our discussions. We are networking folks, so all our kind of upcoming discussions are going to be related to cases where there is at least more than one GPU or more than one GPU server. And this is where I would like to stop for today. And Peter, Jeff, Please chime in.
Since we have only a few minutes left, I just comment real quick. But Nickel was a unique project by NVIDIA as well. But I think in my mind it's similar to NVLink. You must ask, well, we had NPI, like for so many years. Like NPI initially wasn't optimized for GPUs. It was optimized for HPC systems. There were so many versions of libraries as well. I think there was a MVAPage, which is optimized for GPUs over time, and InfiniBand was optimized, but it wasn't public open source, right? So Nickel was initially started as let's write a few collectives, which are so common in ML training, like all reduce only. Well, NPI has like tens of collectives, right? Totally optimized. And optimized for GPU exchange. And eventually it became a full-blown library for message exchanges among GPUs. It became a part of the ecosystem for the CUDA and in general NVIDIA's products. But it's funny enough that there was a product before which we modeled after NPI and message passing, but it was uniquely optimized for GPUs. And what else is important, I think? Among these parallelisms that Jeff mentioned, was the 3 parallelisms, people would argue what model means. Actually, many says model same as tensor. Others says model, it's also pipeline parallelism. But it's a good acronym I often use. There's a paper from NVIDIA called Megatron LM Training. It has this notion PTD, pipeline tensor data parallelism. I often add S there, sequence PTSD, but people don't like this acronym for some reason. But sequence is also about parallelism method, right, for LLMs, by the way. But it's a very good paper. But if you want to read how parallelism is important and how you factor out model to use over GPUs and their power together, it's pretty good to read. And not super heavy, by the way. Some papers are super dense, on ML. It's really hard to penetrate unless you're an expert in this area. But that one was pretty good. But I guess the point was essentially that you have to apply multiple methods of parallelism. Data one is simplest and most essential. When you take the batch of data and slice it into sub-slices, others are more complicated. There you actually slice the model itself, right, into pieces across the GPUs. But then every time, you always slice something. You have to slice the data or the model itself across the GPUs, and effectively you just stretch the model across the cluster. And that's how you get the gigantic computational machine.
So bring an analogy from any different world. We've been talking about network slicing for many years. It never became a thing. This is where it's really important.
Ouch, yeah. It's like that's a strange term. Okay.
Okay. Well.
All right.
Great. I think this is a good place to start, and also a good lead in for our next show. And Peter, I hope you can. We haven't. I hate to put you on the spot on the air, but I hope you can join us again for the next show, because we've as the song goes, we've only just begun. And so one thing I should add, again, for people that are new to this topic, and it's an acronym-rich topic. We've been talking about nickel. The acronym there is NCCL. NCCL for NVIDIA. I forgot what the other C stands for, but Communications Library.
Collective Communications Library.
Yeah. Just for anybody that's wondering, what are they talking about with the nickel? But anyway, thank you so much, Peter, for joining us. Jeff, as always, it's wonderful to see you, and for everybody that's watched and will be joining maybe later on YouTube, thank you so much for joining the show, and we will see you again hopefully in 2 weeks and we'll continue this conversation. Thanks, everybody.
Thank you, folks.
Thanks, Jeff.
Thanks for having me.
Cheers.